Okay, so good morning. Thank you for your being here. I'm Cecilia Metra. I'm very pleased and honored to be here today in Alibaba. Thank you very much for the invitation. I'm the President-elect 2018 of the IEEE Computer Society, and I will be President next year in 2019. And I'm also, in my job, I'm a professor at the University of Bologna in Italy. So a few words about the Computer Society. Our motto is to empower the people who drive technology. We are an international no-profit organization. We have 52,000 members and we are joining professionals and students and academics working in computer science, computer engineering and technology. And we try to bring forward-thinking technology professionals together to discover next technological innovation, develop international standards, create communities, and share knowledge. We are 25,000 members who are geographically grouped in 480 chapters, distributed in 168 countries. So we are really an international organization. We are sponsoring more than 200 conferences per year, actually 210 this year. We are sponsoring more than actually 31 publications, and we are involved in more than 121 standards. Our members are organized technically in the so-called technical communities, which are created around some topics. This is the list of the technical communities that we have, and as you can see, they include a TC on cloud computing, one on learning technology, we have one on dependable computing and fault tolerance, we have the Test Technology Council, which is the council to which I also belong, and we have a TC also on security and privacy. Together with TCs, we recently created also STCs. STCs are horizontal communities, again, of people that address some new emerging issue, topic, technical topic that may involve technically the activity of several TCs. And so we recently created an STCs on big data, one, for instance, on Internet of Everything, one on social networking, and these are all the STCs. So there are different ways where our members can be technically grouped, either through TCs or STCs. I mentioned before, we are sponsoring 14 magazines and 17 transactions for a total of 31 publications. Plus, of course, we are publishing also the proceedings of our technical conferences. These are our magazine titles. They include Computer, Internet Computing magazine, and also a magazine on computer graphics. And these instead are the transaction titles. They include a transaction on big data, transaction on cloud computing, transaction on dependable and secure computing, transaction on emerging topics in computing, for which I'm serving as editor-in-chief this year, transaction on pattern analysis and machine intelligence. So we are actually trying to really cover from the technical point of view with our peer-reviewed publications, all emerging and topics in computer science and engineering. We also have the digital library, which is collecting all our basically publications in transactions, magazine, and conference proceedings. The use of the digital library is included in the student membership, while the other members have to pay an additional fee to have an unlimited access to our publications. We sponsor 210 technical conferences annually. We have more than 60,000 attendees at this conference, and we publish the proceedings of this conference plus other conferences. We also have some educational programs We have some professional competency certifications. For instance, we have professional software developer certification, software developer master certification. We also have some e-learning courses and giving certificates of achievement. We have one on secure software, one on embedded systems, one on multi-core video lectures, and several others which are going to be finalized. We also have an award and recognition program. We have technical achievement awards, and this is the list of the technical achievement awards that we are giving every year. And then we have also educational awards named under Taylor Booth, and one is for undergraduate teaching. And we have also an award for service to the society. We also give student scholarship, more than $40 per year, which unfortunately is not that much, for student scholarship, and these are the 3 kinds of scholarship that we have every year. So basically this is, let's say, all a few words about Computer Society and our activity. I'm here as part of a collaboration that is going on with Alibaba, and I hope we could reinforce in the upcoming years our collaboration and common interest. Okay, so now I would like to talk to you a little bit about research challenges for electronic circuit and systems in the Internet of Things era, which is a topic where I work on as a professor at the University of Bologna. Just a few words about my university. It's the oldest university in the Western world. It was founded in 1088. It is among the top 5 Italian universities on the main international rankings. It is actually the largest one in Italy, and it is the second one for the funds received by the European Commission. And it has 5 campuses, 11 schools. I'm a professor at the School of Engineering and Architecture, and we have 32 departments. We have 12 research centers, now 85,244 students, and students are approximately 1/4 of the whole population of the city, so it's really a very young university city. And we are approximately 6,500, 1,900 staff, teacher and staff, so half of them are teaching people, just like myself, and half of them are administrative people. And we receive, as again, some fundings from European Commission and also as well from companies. And we had famous professors and students, just like Dante Alighieri, Copernicus, Galvani, Marconi was from Bologna, so several famous people. So what is my research group? So basically I'm working since more than 25 years now at the University of Bologna, with a main focus on tests, online tests, and fault tolerance approach. And I will present to you some more details about this. And this research has been conducted, also funded and in collaboration by Intel Corporation, Philips Research Labs, the European Union, again, Aston Transport, ST Microelectronic, the Italian Space Agency, and several universities, and I've been funded also by the Italian Ministry of Research. And I'm also more recently, we started working on energy efficiency and smart lighting, also funded by a company in Italy whose name is Beccaro Beghelli, and funded by the Italian Ministry for the Development, for the Economic Development, and worked also a little bit on security, again funded by the same company and ministry. So what about some more details, and then we will go to the topic of today on our research in tests, online tests, and fault tolerance. We worked in this field for high reliability applications, and we worked in collaboration with the Simon Fraser University in Canada on high reliability energy harvesting systems for biomedical applications. Then, in collaboration with Becker Beghelli and the Italian Ministry for Economic Development, we worked on communication protocols for secure wireless sensor networks for the lightening of big geographical areas, just like stadium and so on. In collaboration with Stuttgart University in Germany, we worked on self-checking design and diagnosis approach for automotive systems. Self-checking approach is an approach to guarantee high safety and reliability that will be mentioned also later. In collaboration with ASSO Transport, we worked on control systems for train, and again, checking implementation of control systems for trains. Collaboration with the Italian Space Agency, we worked on modeling the soft error vulnerability, and we will talk more about soft error in a few minutes, because they are also nowadays a risk for reliability of electronic circuits for electronics on board of satellites. And then with the Italian National Institute for Astrophysics, we again worked for space application on another fault-tolerant approach, and particularly low-cost, reliable, redundant systems. Instead, in the field of test, online test and fault tolerance for general-purpose applications, in collaboration with Philips Research Labs and funded by the European Commission Union, we worked on the development of error-correcting codes to reduce the power consumption, the crosstalk noise, and the power supply noise on basis of high-performance systems. Then funded by ST Microelectronics in both Italy and later in France, we worked on several issues: reliable design, a tool for the reliable design of integrated circuits, a software tool. We worked on hardware reconfigurations, hardware reconfigurable systems, and we worked on the implementation and analysis of the reliability of interconnects in 3D stacked chips, and this was a research that we conducted almost 10 years ago now. And then in collaboration with Intel, funded by Intel Corporation in US and Europe, we had several research going on since the year 2001, when I was visiting faculty consultant for Intel in the US. And we worked a lot on clock faults modeling and clock faults reliable distribution within high-performance microprocessor. We worked on the innovative approach for a reliable control logic, a low cost. We worked on power droop during LBs, which is a testing approach. We worked on power binning, and also we developed a tool for the evaluation of the cost of implementing error-correcting codes for multiple bit offset in cache memories. Then in collaboration with Northeastern University, we worked several years ago on emergent technologies. So we worked on the reliability, defect modeling, and reliable design of buses implemented by carbon nanotubes. In collaboration with Georgia Tech University, we worked on, again, analysis of soft error vulnerability, which is a reliability risk, and transistor sizing, which is an approach to deal with this risk. Then more recently, we worked on monitoring MBTI effect, which is an aging phenomenon. We will talk about this in a minute. We worked on the mutual impact of soft error and aging. And nowadays, we are also working on fault modeling and tolerance for resistive memories, mainly phase change memories. So this is just a broad, let's say, list of the specific research issues we've been working on in these years in collaboration with some companies. So in this talk today, I would like to basically quickly address some of the major reliability challenges for our electronic circuits and systems nowadays. And I will briefly go back to the development of microelectronic technology till now to arrive to address the reliability challenges for today's electronics. And particularly, we will talk the main challenges are due to the so-called transient faults and the possibly originated soft errors and aging phenomena. And we will address them in a little bit more details. And then we will quickly review some of the design approach, hardware approach that can be used for reliable electronics to deal with this, to avoid that this phenomena could compromise the correct operation of electronics in the field. I will quickly recall the approach for hardware fault tolerance, and I will present some solutions that we developed at the University of Bologna, mainly to deal with soft errors in memory elements and aging phenomena on data paths. So let us start from a quick review of microelectronic technology development till now. So we know that we assisted to a continuous miniaturization of microelectronic technology. That is what enabled nowadays massive diffusion of electronics that is surrounding us. Electronics that now is connected, all electronic devices are connected to each other through the internet, creating the so-called Internet of Things. So the huge amount of electronics that is connected to each other is providing a big amount of data that have to be stored, processed, and distributed again. And we are talking about 1.5 gigabyte of traffic per day due to internet users, 4,000 gigabytes per day every day due to autonomous vehicles, 3,000 gigabytes per day due to the smart hospital, 40,000 gigabytes per day due to airplane data, and 1 million gigabytes per day due to smart factory. You may have different statistics, but anyway, this is really a big amount of data. And so we have our life decisions that are more and more driven by such data, which are probably can be exploited for machine learning and decision taken by artificial intelligence. And we may think about autonomous drivers, smart factories, smart home, transport systems. And so an obvious concern that arises is, but are these data that are generated, processed, and distributed again reliable? Can we trust the correctness of this data, which even before means is the electronics that is generating, processing, and distributing again this data reliable? And so this is the issue that I'm quickly trying to address. So as known, the technology, microelectronic technology evolved following the Moore law that predicted that the number of devices per chip would have been more than double every 18 months. And nowadays we are approximately at 10 nanometer CMOS technology. Some companies are already into massive production of 10 nanometer technology, other claim they will go into massive production next year, but this is where we approximately are. But we started, let's say, almost 50 years ago from 10,000 nanometer technology. So the evolution that we had in terms of miniaturization has been really dramatic. And this took place by following the Moore law. But following the Moore law by all semiconductor companies basically has required to implement several changes. Starting from the year 2000, we assisted to an architectural change, at least a microprocessor. The multi-core and many-core systems started being adopted by basically all companies. And also since the year 2007, we assisted to some material change. They changed the insulator of the gate of the transistors. And starting from the year 2011, especially companies producing high-performance electronic change also the devices, the 3-gate or FinFET transistors started being used. In a little bit more details, since the year 2000, we assisted to the use of the multi-core or many-core architectural paradigms. And this is a trend that also according to the prediction of the IEEE Computer Society 2022 report, which was done in 2014, will continue in any application field from, let's say, servers to robotics, entertainments, biomedicine, and so on. And as I mentioned, since the year 2007, we also assisted to a change in the material. So they started using several semiconductor companies a so-called IK insulator for the gate of the transistor that compared to the traditional CO2 insulator enable to increase the intrinsic capacitance of transistors, and it was reported that it enabled an increase of the 60%, which means that it provides faster transistors. And also this new insulator was enabling a reduction, it was claimed more than 100 times reduction in the leakage current through the insulator, thus giving rise to less power-hungry transistors. So reduction in power consumption and increase of speed, in a simple way, in simple words. And also, starting from the year 2007, most semiconductor companies for high-performance electronics started changing also the device. Rather than the traditional planar transistor, they started using the 3D or FinFET transistors, where we have an increase of the channel width, which is basically surrounding this fin. And so this also enables to have, so since we have longer channel widths, we have faster transistors, and it is reported an increase of possibly 37%. And these transistors also have been proven or have been claimed to provide a lower subthreshold current, IOF. So again, they are less power-hungry transistors, 50% reduction it was reported for some examples by some companies. So all these changes have enabled to basically keep on increasing, keep on scaling down microelectronic technology, thus increasing integration density, and so enabling more complex, let's say, computations, and increase the performance. And all of this increasing complexity, computation complexity and increasing performance is what basically enables what we see nowadays with this massive distribution of electronics objects connected to each other and exchanging data that can actually be elaborated real time and distributed again through the Internet of Things to actually benefit, I would say, our lives. But all this development came always together with some, let's say, challenges, and in particularly we had challenges also for test. Test is the process that is verifying that every chip is behaving as expected by design, and every chip which is fabricated needs to be tested prior to be introduced into the market. But also, and this is what I would like to talk today, challenges for the reliability, so for the correct operation in the field of these electronic circuits. And which are those which are recognized to be the major challenges for current scaled down technology from the reliability point of view? There are transient faults and the possibly generators of errors and aging phenomenon, particularly the so-called bias temperature instability. As we will see, they may compromise the correct operation in the field of our electronics, so the data that our electronics are generating or are processing may be incorrect, but we will see there are solutions that have already are in place and solutions that are developed in order to guarantee that despite these problems, our electronics can operate in a reliable way, which is particularly important nowadays. So what about this increased vulnerability to transient fault and of errors? So transient fault, as you may know, are undesired voltage fast transitions, so glitch or spike that may occur on a circuit node or line. They are generated by alpha particle hitting the silicon. Alpha particles are atoms of helium that lost the electrons, and that can be generated by the radiative decay of unstable isotopes present within the package of the electronic circuits. Or these other possible cause of transient faults are also neutron and protons originating by the sun activity, basically by the collision of the so-called galactic cosmic rays and atmosphere atoms such as nitrogen and oxygen. These transient faults have always been a problem for space applications, for avionics, But they started become a problem for general purpose electronics when we start moving, I would say, below the 100 nanometer technology. And they are more and more a problem as much as we scale down technology. And what is the problem? The problem is when this voltage switch, for instance, are sampled by a latching element and give rise to a logic error at the output of a sampling element. So one big issue and concern has been what happens if a transient fault is affecting a combinational logic within, let's say, a data path. We can consider this ending part of a very simple data path. So what happens is that if we have a particle hit, for instance, due to an alpha particle in this node, and we generate a spike here, the problem is if this spike propagates till the input of the latching element and is sampled in such a way that a logic error, which is called soft error in this case, because the cause of the error is a transient phenomenon, a soft phenomenon, is generated. When can this happen? So for this to happen, it is necessary that the spike, which is locally generated here, is not electrically filtered by the logic gates on the paths from the node to the latching element. In addition, it is also necessary that this spike that can propagate till here is not logically, we say, filtered out, but the gates which are on this path. For instance, if this input is equal to 0, of course we have a high voltage value here, no matter about what you have on the other input. So we talk about electrical filtering and logical filtering. If it's not even logically filtered, it will propagate till the input of the latching element. And so at this point, if it arrives at the flip-flop input with a spike that is satisfying the setup and all conditions of the flip-flop with respect to the clock sampling edge, then an output logic error, that is a soft error, may be generated, which is a logic error that we have within our system that could consequently compromise the correct operation in the field of our system. So a soft error may be generated if we have a transient fault affecting a node within a combinational block if all these ifs are satisfied. So there is some likelihood, we cannot neglect the likelihood that a soft error is generated, but generally it is considered that it's not a very likely event. More risky is the situation when the transient fault is affecting one node within a latching element. For simplicity here, we can have a naive, straightforward latch. And especially when this transient fault, this particle hit, is affecting the node before the feedback loop of the sampling element. In fact, in this case, if this happens, basically we, for instance, if we have an alpha particle hitting this node during we can assume it's a clock semi-period during which the feedback loop is conductive. So the incorrect voltage value, which is generated on this node, can then be propagated to the output and be confirmed by the conductive feedback loop, so that basically we have a logic error at the output of this latching element. But assuming that we have a squared clock, we have half of the clock period during which any alpha particle or neutrons hitting this node will generate a soft error. So it is very likely that a soft error is generated due to particle hits affecting the internal nodes of latching element and flip-flops. This is why semiconductor companies usually design the so-called robust implementation of latches and flip-flops to be used within their electronics, because these blocks are really likely, if affected by particle hits, which cannot be neglected anymore, to give rise to outputs of errors. And we also worked on some robust design of latches and flip-flops, and just I will quickly mention some of the solutions that we developed ourselves. But before going to this, let us address the other reliability risk for today's electronic, which is basically the aging due to bias temperature instability. This is the phenomenon which is recognized the most likely aging effect for nowadays electronics. And it can take the form of the so-called negative bias temperature instability when it is affecting PMOS transistors, or positive bias temperature instability when it is affecting NMOS transistors. And basically, in both cases, it creates an increase of the absolute value of the conduction threshold of the transistors, so that basically the transistors become slower than expected without aging. And the problem is that this phenomenon occurs in the field. It gets worse with usage of these transistors. When the transistors are not used, we have a partial recovery, but again, it's a partial recovery. It is not a full recovery. And it has been reported, for instance, that MBTI can degrade of more than the 20% in 10 years the performance of an integrated circuit. But the problem is that we cannot predict where it occurs. It may affect some transistors of the die and not affect others. And it's a slowing down of the operation of the circuits in that area of the die. And if this slowdown is depending on the entity of this slowing down may also give rise to the sample of incorrect data, so again causing logic error and compromising the reliable operation of our integrated circuit in the field. And especially for this kind of aging, we will see there are some solutions which mainly consist in using monitors, integrated monitors on the die. And we also worked on this, and I will show to you in a few minutes some of the solutions that we worked on in this field. So if we go to, the main issues for current electronics reliability are basically transient faults and the possibly generated soft errors, and aging phenomenon, mainly BTI due to aging. Which are, let's quickly address which are the possible solutions. Of course, please ask to me if you have any question, any clarification, you can interrupt me with no problems. So which are possible solutions? So one approach for which is frequently adopted is hardware fault tolerance. Hardware fault tolerance can be successfully adopted to guarantee the correct operation in the field of our electronics, and especially it is a solution to deal with the soft errors possibly due to transient faults. The traditional hardware fault tolerance can take the form of modular redundancy or online testing and recovery or error correcting codes. Error correcting codes can be used in memories and in buses, so where basically there is no elaboration from the, let's say, transmission point and the reception point, while modular redundancy or online testing and recovery have to be used in logic when we have elaboration in between a transmission point and the reception point. Modular redundancy, as you may know, has been frequently adopted in space application, is currently adopted a lot also in avionics and transport systems. But for general purpose applications, usually in commercial application, it is not adopted that much because it's very expensive. So it implies to at least replicate or replicate n times a basic module that can occur at any level. It can be a whole microprocessor, a whole system, or a simpler logic. And the outputs of, for instance, the triplicated versions are given to the input of a voting element, which gives to its output the logic value present on the majority of the inputs. So this is an approach to guarantee the tolerance. So if we triplicate, for instance, a module, we are able to tolerate the faults affecting a single module. Then usually it is implemented in the n-modular redundancy form. We have some inherent, let's say, detection approach that are integrated that enable to realize that a module is faulty and then the module is replaced by another replicas and so on. But the concept is very simple, even though the true implementation is not straightforward. We need to use design diversity because we may have common mode failures. So in practice, there are several issues that needs to be addressed. But this concept, just as a general reminder, is very simple. An alternate for logic is to make use of online testing and recovery, where online testing is a way that through which we call all approach that guarantee that testing is performed continuously during the normal operation in the field of an electronic system. So as soon as an electronic system gets affected by a fault, an alarm message is generated so that proper recovery approach can be activated, that can be used to mask or correct the effect of the fault, so that overall the user doesn't realize about anything and the correct operation is guaranteed in the field. And online testing can be implemented using either self-checking circuits or the application and comparison. The application and comparison is quite more expensive, so generally in general purpose applications where we want to limit our cost, we use self-checking circuits. And for instance, data paths of several high-performance microprocessors are protected using self-checking circuits and particular kind of codes. And then recovery is implemented at the software level and system level, so that we can guarantee the correct operation in the field with the user not realizing about any transient faults which occur during the normal operation and possibly generated soft errors and also other kind of faults that may occur in the field. And as I mentioned before, recovery is the term through which we call all approach that can be used to basically reestablish the correct operation after the generation of an error message by the selected online testing approach. Finally, error correcting codes also, as we all know, they require information redundancy. They are frequently adopted, I would say, for memory, standalone memory, embedded memories, cache in microprocessor, and basically we write a word which is encoded by means of an error correcting code, and when the word is read, it is basically decoded and corrected by some hardware blocks that implement the error correcting code on the die, so that the corrected word is then given to the output. And ECC are also frequently adopted on buses, and the principle is the same. We transmit a word encoded by the ECC, and at the receiver point of the bus, we basically decode and correct properly the word which is received, in order to guarantee that what transferred to the fan-out logic is actually correct. Okay, so this was just to quickly remind the traditional hardware fault tolerance approach, of course, especially for, let's say, general purpose electronics, very specific high reliability approach can be, and have been devised and can be devised to deal with possible soft errors and to deal with aging phenomenon. Usually the goal is to guarantee lower costs in terms of error overhead impact on performance of our system compared to the traditional approach, but of course basically all approach typically implies some form of redundancy. We can have a look quickly just to have an idea about, to look at some robust latches design that we worked on, and what I will show has been published in 2010. So basically the idea to make a latch robust with respect to transient faults hitting the internal node prior to the feedback loop, which is the most critical one, and that is to avoid that the output can change due to particle hitting the internal node, has been basically to triplicate this internal node and to make the output change through a so-called C element, which has been used a lot also in subsequent research, to make the output through a C element change accordingly to the majority of the internal nodes. And so the idea is that since the transient fault will affect a single internal node, the output could not change due to a transient fault affecting a single internal node, because the output will change based on the majority of this triplicated internal node, and a transient fault can only affect one out of the three internal nodes. And so this latch was able to tolerate by design, we can say, internal transient faults. So transient faults affecting the internal node will not change the output, so will not give rise to soft error. So transient faults are tolerated by design. And we compare this robust latch with respect to another robust latch that we published before in 2007 here, and with two other robust latches published by other colleagues. And what we found out is that compared to our previous robust latch, our previous robust latch, transient faults for all these three kind of latches, transient fault on the internal nodes were tolerated by design, while in this robust latch, transient faults on the internal nodes could create an output of error. And in our previous solution, however, we could have outputs of errors, while in these three solutions, we could have no outputs of error. So compared to basically this other design, which is providing the same robustness with respect to transient fault, the solution that we propose requires lower error overhead and significantly lower, 27%, more than 27% lower impact on performance. Compared to this other solution, which however is less robust with respect to possible outputs of errors, we still enable lower impact on performance, but we require more area, more power and more area. And compared to our previous solutions was cheaper, almost the same impact on performance, but less area, less power, but it could present outputs of errors, so was less robust. Anyway, this just to give you an idea, there are several robust latches which we worked on, and that have several colleagues and companies have their own patented robust latches and so on, several which have been proposed in the literature. All of them can achieve a different trade-off between robustness and the cost. And of course, depending on which design, you may decide, okay, to put a robust latch with higher impact on performance only on short paths, while it may be more robust, while on longer paths you prefer to have latches which have very minimal impact on performance, and maybe you renounce to robustness if needed. Because again, an issue is that you don't know where this transient fault may occur. There have been companies did lots of analysis, semiconductor companies, in these. Latches are critical components, everyone agrees on that. And so they use different designs on different parts of their high performance reliability. Okay, this was just to give you an idea about something that we did. What about aging monitors? So we also, I would like to show you very quickly one aging monitor that we worked on and that we published in 2013, initial version 2010, and then, 2013. So it is a monitor that can be connected to the input of the flip-flops at the outputs of data paths in order to detect possible late transitions of these signals due to aging affecting the circuit. And one issue is to discriminate delays due to aging with respect, for instance, to delay faults. And so in order to do this, we did some analysis and we identified a time guard band during which, if a late transition occurs, this can be recognized as due to the initial effect of aging phenomenon. And basically, we developed this monitor, which is able to generate an error message, which, as typical in high reliability systems, is either a 0, 1, or 1, 0. If there is a delay due to aging which occurs during this time guard band. Otherwise, it generates an indication of correct operation that, as typical in high reliability systems, is 1, 1 or 0. And so basically, again, compared to previous monitors of this kind that had been proposed by other colleagues, at the moment of publication, this monitor was requiring, again, less area and some improvement, less power also. This is our, with respect to the previous one. So it was more convenient from the point of view of cost. And again, so once so the idea of all these aging monitors is to monitor in the field the initial occurrence of some delay effect due to aging prior to this aging, which is getting worse and worse with time, to create a delay effect which could give rise to a logic error, thus compromising the reliability of the system. And then once this initial early monitoring, we can say, of aging is detecting that we are starting having some problem, proper, again, recovery approach can be activated. A straightforward one is to slow down the frequency of the clock so that even if the signal is delayed, we will keep on sampling a full signal. And also we worked on other approach, which are more a correction approach to avoid the reliability risks due to aging. Then something that we worked on more recently has been to analyze the impact of aging on the soft error vulnerability of integrated circuits. And we analyze this for combinational logic, sampling elements, and here I have the results for latches. We analyze the impact, how, let's say, aging may impact the likelihood to generate soft error, which is usually measured by the so-called SER. And we analyze that for a standard latch, the low-cost robust latches that have been proposed, and the highly robust latch that I presented before and that we worked on, that we published in 2010, I think. Yes, 2010. So the one that I just showed. And basically, as obvious, as expected, but we proved that, what came out is that aging is worsening the vulnerability to soft errors of integrated circuit. So due to aging, for all latches, and these are the graphs reported here, basically the soft error rate, so the likelihood to have a soft error at the output of the latch, is increasing for all latches. While, okay, in the case of the latches that we proposed in 2010, they are more than 2 orders of magnitude less vulnerable to soft errors than the previously presented latch. And what is positive in this latch is also that we can see a slight increase with time, while for all other latches, especially in the first 2 years of operation, we have a more rapid increase in soft error rate, and then we have some sort of saturation. But what, independently of the comparison of one latch to the other, what I think has been interesting in this research has been showing that the robustness of our latch changes over time due to aging. And since we can no longer neglect aging, and with continuous scaling, aging is becoming more and more a problem, the problem is that even when considering the robustness with respect to soft error, we need to account for aging. And usually, instead, in all modeling for soft error vulnerability and so on, we were considering only instant t equal to 0. We were not considering the aging of transistors. And so after this research, then we, of course, worked on dynamic models for soft error vulnerability, and also from the point of view of robust design, we worked on solutions which were able to mitigate the worsening of soft error, of the likelihood of soft errors due to aging. And one of these solutions has been, we recently published, has been only published on online already, and the basic idea is to modify the internal structure of standard and low-cost robust latches in order to reduce the stress time of the transistors driving their most susceptible node. Reducing the stress time of the transistors, we reduce the aging of these transistors, And so the delay effect due to this aging and consequently the increase in vulnerability to soft errors of these latches. And so basically we applied our approach to some already proposed latches that were presented before, and we found out that basically we are able by this approach to reduce by the 50% the increase in soft error rate due to aging, due to basically BTI, base temperature instability in these latches. Anyway, this is just to give you an idea about, so mainly soft errors, and these are the cost of this approach, which are not, okay, 10% increase on average in air overhead and 5% on average in power consumption. But we reduce of the 50% the soft error rate. So anyway, basically, so to conclude, transient faults and possibly generated soft errors, as well as aging, are currently recognized as a major attempt and risk for reliable electronics implemented by today's scaled down technology. But the positive is the aspect is that there are solutions to face this reliability risk. Hardware fault tolerance is an approach that has been traditionally adopted in every high reliability applications, that is also adopted in consumer electronics. Hardware fault tolerance is a solution for soft errors and possibly due to transient faults. And for aging, another solution is to implement appropriate monitors on the die to guarantee the correct operation of electronics in the field. And together with this, I mean, all variations of this possible approach, there are several innovative approaches that have been developed in the past, that are currently under development by the researchers working like me in the field of reliable design of electronics. And so there are several solutions to address these issues so that we can actually trust the reliability of our electronics to store, process, and distribute again all the big data that are currently generated by the Internet of Things, so that actually we can exploit this data to improve our lives. That's all. Thank you very much for your attention. I don't know if you have any question. It has been a very general presentation. If you have any question or... Yes. Okay, so I can be more detailed. The question is for those, if someone have not heard online, why scaling down technology, so smaller size, is increasing the risk for reliability. So for transient faults, what happens is that if we, so basically, okay, so if we reduce the transistor size, if you consider a combinational logic, just two gates connected to each other, if you reduce the transistor size, the capacitance that is associated to the circuit internal nodes, that capacitance is representing the output capacitance of the driving gate, the input capacitance of the driven gate, and the wire capacitance. So if you reduce the size of the transistors, the capacitance associated to the internal nodes is diminishing. So it is easier for a particle hitting with the same energy as before. So for larger transistors, if then you reduce the capacitance, a particle hit with the same energy if the capacitance associated to the node is diminished, is able to make the voltage associated to that node change more with respect with what was happening with previous technology. Okay, so the same energy associated to a particle hit affecting one node. If the capacitance associated to the node is smaller because the transistors are more scaled down, For the same energy of particle hit, basically you create a glitch which is higher in amplitude and also wider. Because what happens physically is that you have a particle hit, the particle is penetrating the substrate of the silicon and is generating electron hole couples. And these move under the effect of the electric field towards, so electrons towards higher potential and holes towards lower potentials. And so they change the charge, the charge region that you have across the diffusion of the drain and source. And as a result, you have a change of the voltage associated to circuit nodes. And the more energy, so if the energy is the same, on principle, you have the same entity of electron holes that are generated. But if the, let's say, the capacitance associated to the node is weaker, for the same charge which is injected on the node, you are able to create a higher transition and wider transition. So you have bigger glitches. So before, with scaled down, less scaled down technology, basically these spikes were so low that they were immediately filtered out electrically by the fan-out gate. Now they are higher and they can propagate through various stages till arriving to the input of a latching element. So basically the issue is that with scaling of technology, you are reducing the charge, as the capacitance associated to the internal nodes is reduced. Then you are also reducing the power supply, because with scaling you scale down VDD as well, and so the circuit noise margins also diminish. So with respect to previous technology, it's more likely than, again, you generate at the end a soft error due to a spike that propagates. So the issue is that with scaling, we generally say you reduce the capacitance associated to internal nodes and you reduce the VDD. And due to these two phenomena, basically you have a spike that may result in soft errors also at the ground level. Because before there had been a problem for high altitude, because of course since particles are generated from the sun activity and so on, the energy is higher when they hit the electronics which is on board on satellites or in airplane. But then with scaling down of technology, they became a problem also for ground level. So basically, even if the energy is low, due to this phenomenon that comes together with scaling, the entity of spike which are generated may compromise the reliability also the ground level. And so actually, I mean, high-performance microprocessors are internally protected. The cache are using ECC and also data paths. Some companies claim these are protected with respect to this event. And they are becoming worse and worse the more we scale down because of the same reason. Okay, thank you. Is there any other question? Or well, this approach, the hardware fault tolerance approach, so some of them, as I mentioned, are used also in massive production of general purpose electronic, high performance microprocessor and so on. You can use in any products that you like. Of course, the issue sometimes is to develop specific solutions that imply a very low cost. So some of the techniques that we've developed with some companies, for instance, to protect some parts of some systems, the target was to have an area and impact on performance increase of 0.5, 0 point some percent, so it was very low compared to the traditional solution. So the issue is usually the cost, but so they are basically design approach. So usually once you decide that you need to use them and you decide to use them, then you integrate them into your design, and that's it. It's not that they require, I mean, once you devise the approach, then they can be implemented in a very standard way. So they can be automatically implemented into the design flow. So it's not that they imply an increase in the design flow, increase of time in the design flow. The issue is whether you need that, and if you need that, to find out the solutions which are more appropriate for your market, basically because the cost they involve is low and so on. But as I mentioned, they're more diffuse than one may think, because really these issues seems to be an issue also for 1-2 years of operation. So this phenomenon may compromise the correct operations of products in the first years of operation. So even products that have very short time of, let's say, life. Thank you. Thank you very much. It's been really a pleasure and honor for me to be here with you. Thank you.